Hello, I'm Hannes. I'm from the University of Cambridge, and I'm here to present Not Quite So Broken TLS, which is joint work with David and Peter and Anil. So I won't talk in detail about TLS, the protocol itself, because I think it has been covered in earlier talks. But I will motivate my talk a bit by looking into a specific TLS implementation, which does a specific job called SSL 2.3 get client hello, which receives some SSL thingy, and then does a bunch of things. I will briefly scroll a bit through it and look a bit how the code structure is. Well, we have some conditionals, that's expected. Also, please keep in mind the return value. The return value of this function is, or this method, is an integer value. So whatever you expect from it, there's also some conditional compilation going on, and there's still a bit more. State has several go-tos and does a lot of things at once. I claim that this function is barely testable because you need to know about all the world, I mean all the heap the actual program has in order to try to do anything in here. So this is, oh, that's the end. Great. So certainly this is only a small example in existing system software. I'm not claiming that it is true for all the system software. But we analyzed actually common vulnerabilities in various TLS stacks and the most widely deployed over the last year. And we discovered that the sources of those vulnerabilities were to a large extent memory safety. So memory safety means that you get out-of-bounds accesses of certain buffers. Then state machine errors, well, Yuri was explaining in detail what that means. And then certificate validation and ASN1 parsing were also pretty, well, quite some problems. So a well-known problem for memory safety was Heartbleed last year. For state machine errors, it was maybe the early change cipher suite. Certificate validation and ASN1 parsing, well, there was at least one bug in NSS which was a bit loose on parsing the algorithm identifier subfield, and you could insert some garbage in there. The problem here with, for example, with certificate validation is that nowadays system software and nowadays software does not really separate between actually parsing of the certificates and validating them. So you have a rather convoluted code base which combines all of them into one and does the message passing or the communication to other methods via the shared mutable heap. So that is a bit unfortunate, a bit sad in a state. But while all these CVS sources can always be blamed to either an individual who wrote the code, or several individuals who didn't review properly the code, or so, we state some root causes of those problems. And the main root cause is the usage of error-prone languages, such as C in the systems community, which doesn't give you a lot of abstractions, which needs you to write a lot of boilerplate in order to implement a certain algorithm or protocol. In order to do that, you have to write a lot of boilerplate, and then your code becomes a lot of convoluted, and you cannot easily read the C code, the written down C code. Also, the programming languages used in those systems clearly lack a lot of separation of concerns, because they don't have an abstraction features. They lack a lot of different abstraction features which are popular since the 80s. And another problem with protocols such as TLS is that it is specified as an ITF RFC, so as a request for comments. TLS contains or is specified in several RFCs, and that gives roughly 30,000 lines of English prose, which is very ambiguous. You can interpret it differently. Also, it is not testable. I mean, the RFC is just a piece of English text. There's no test suite around. So what people who implement TLS usually do is to do some interoperability testing, which means positive testing. Oh, my stack can talk to those 3 other stacks. Oh, that's fine. Let's release it. But negative tests, like regression tests, like I don't have a heartbleed failure, is barely done.
So what do we do to handle those alleged root cases? Well, causes. Whatever we can to tackle them head on. First, we change the language and use a particular choice of the concrete language and its idioms, more on which in a little. We also code ground up for maximum separation of components, achieving as much modularity of parts of the actual implementation as we can. At the same time, since we lack an actual truly precise and ideally machine-usable specification, we were aiming to build one. So we're writing code from the ground up to be reusable as a specification and as an implementation. And it's basically the same code. So our implementation side, and it's should we prove that it robustly interoperates with the rest of the world and with the implementations out there in the wild, it goes to show that our interpretation of specification is also reflects what other implementers think that the actual specification is. About this choice of language, it's hard to overstate how important choice of language really is to help prevent a large body of software from caving onto itself. We're using OCaml here, which is a memory-safe language, including garbage collector, and it has an expressive and static type system. And we use it in a particular way, which means that we mostly don't use side effects. By side effects, I mean either changes to shared bit of heap or non-local exits and non-local control flow. So this yields to very explicit flows of data because all of the data flows can only be mediated through passing and returning of arguments to and from functions. This also means it is value-based in the sense that we don't talk about locations with change or objects or something. We talk about little descriptions of the information state at particular points, which we call values. And we use in-band error handling, which means it is explicit and it has to be accounted for. In fact, even the compiler checks this. So this is a laundry list of some of the ways we use, in which we use OCaml, but people usually call this list purely functional programming. So what we're really doing here is using OCaml in its functional mode to try and contain the usual problems inherent in programming language when implementing something like TLS. Why would we do that? Because it allows us to raise the level of abstraction significantly, and of course it helps us with some of the automated resource management. So in this way, just by switching the language, we avoid large amounts of what can be described as incidental complexity inherent in all the code bases I've been through, at least, which are all of the widely used TLS implementations. As an aside, there are more formal approaches to the problem of making a high assurance, high confidence TLS stack. Some you heard a little on that topic just a while ago. They usually either try to reason about a simplified model, a model of TLS extracted from the actual implementation, and then it's not clear what the relationship between this model that's been reasoned on and the actual implementations in the wild, or they try to reason about parts of large in the wild bodies of code, but they tend to reason about relatively small parts. We still have to see a large, formally verified implementation of the entire stack, and it is not clear what is there to really verify because we don't even have a machine-usable specification. We don't, in a formal way, know what TLS is. So we are not these guys, although we sometimes get confused for them. Yeah, what we're trying to do is actually arrive at a completely deployable TLS implementation, something we can run. So what we have is what we call nqsb-TLS, and it's a full TLS stack from scratch, and we made it to fulfill two purposes: to at the same time be a specification, which can be run to check if something conforms to it, and as an actual TLS library that we can use to communicate over the internet. So this is broadly structure. This roughly shows the breakdown of sub-libraries involved in our TLS, and there is the actual TLS state machine encompassing all of the protocol, core protocol logic, and then there's the part which deals with X19 certificates and their validation, and then there's a separate part which deals with SN.1, and we also have a crypto library which also contains a random number generator, and this is the core stack. It needs to be glued on top of something called the flow interface, which provides the actual network interaction. It needs to be provided with entropy and maybe configuration and similar stuff to actually work. Now, this kind of looks fairly trivial, yeah, but this is how TLS actually decomposes. This is our actual layout of modules, and as far as I've seen in the wild, code bases implementing TLS, they don't look like this, really. They don't actually have those parts completely separate. Relatively specific feature of the core protocol implementation is that the core is, as said, purely functional. The entire protocol basically boils down to two externally facing entry point functions, and you're seeing the type for one of those two, the reactive one, which receives a buffer and does something to it. And the type shows you that it takes an opaque value, an abstract data type representing so far accumulated state, a byte vector essentially, and returns either a failure with its own after data type, or success with a state, and maybe a buffer intended for the application to consume, contained in application data frames, or, and potentially a buffer to send back onto the network. Now, the real important thing is to note is that this and this state are not one and the same. It doesn't change it. Instead, it takes a state and maps it to the successor state given a particular input buffer. So the entire protocol unfolds as a sequence of maps from the previous state value to the next state value mediated by the incoming buffer, and this is actually contained in a wrapping shell which combines this pure stack with something that can talk to the network. In other words, the problem of maintaining this state and knowing where it is completely localized to the outermost shell. Everything inside of it is dealing only with values, and we can, for example, take a state and rewind back to it because we're not changing it. This is a small snippet illustrating how, in particular, OCaml goes to help with implementing something like TLS. This is a part of handshake handler, which, given a session state and a handshake state, and the incoming buffer needs to decide which transition to take. And this may be interesting given the previous talk, or two talks ago, about failures in state machine logic, which is also quite prevalent. What you can see here is that after parsing, we have to account for the potential of error, otherwise compiler warns us. If everything is successful, we have to somehow scrutinize the session state value and the handshake value. And this is the only way to do this. This construct in OCaml combines checking for the particular structure of values, like this and like this, with branching. So what we effectively have is a list of combinations. If we are in this state, and this is the decoded incoming message, then this is what we do, the result of which is just the next state value. Or if we have this state, and this is the incoming message, this is what we do. One thing to note is that the entire value propagation is completely explicitly done through this state of value. So we can neither facilitate values out of thin air, which means we cannot, for example, enforce null secrets if we get out of order change cipherspec message, because we don't have them in no shape or value. And we also have to decide what goes where. So instead of kind of implicitly relying on a combination of things which were maybe initialized and maybe in different shape. So we have a very clear description of kind of the state machine transitions. It's not by itself formal, but it's incredibly usable from an implementer standpoint. This is another example where OCaml helps us. This is SN. SN.1 is quite nicer to deal with. There are even suggestions that signatures encoded in SN1 should be verified not by parsing and then comparing, but by constructing another SN1 record and comparing the results, because SN1 is allegedly dangerous to parse. This is the formal language of SN, which is either used by compiler, which generates the parsing code in target language, or much more frequently, manually implemented in the implementation through more or less an ad hoc parser. This is our code which implements this grammar. It more or less corresponds one-to-one to the actual SN1 formalism. Of course, this code doesn't actually go through the bytes, but the code that goes through the bytes and does the SN.1 decoding by itself is then completely isolated and very small. And this is the rest. This is the information needed to convert that into a particular parser for a particular structure. So it's one more way in how the level of abstraction we can get from OCaml helps us. A snippet of X59 validation code, which mostly shows that it looks like a bunch of predicates. This is basically a conjunction with a little more detailed error reporting. All the validation code composes like expressions as opposed to forward-running programs. So we have no control flow, no go-tos, and everything looks more or less like this, which is helpful. We had to do our own crypto. As a detail, we have cipher cores and hash cores written in C. On top of that, cipher modes, the ones we have, counters, CBC, even GCM and CCM, are written in OCaml to contain the complexity as much as possible. And we also redid the public key, mod P public key cryptography, and we did that in OCaml using GMP as the big num backend. And then people always ask us, what do we do about timing? More or less everything everybody else is doing if they're trying to mitigate for it after the fact. So we're using SNI for AES processing, which is, according to Intel, constant time. So doesn't open up for the timing sidechain link call in the normal AES implementations have, or sometimes have. With blinding for mod P public key crypto, more or less the same way other implementers do that. On top of that, on higher levels in PKCS and in the actual protocol, we just have a collection of different specific mitigations which other people have come up with and described and agree upon or so. And as a detail, we don't still have a mitigation for like a 13, but we're working on it.
Okay, now we have seen actually our implementation of it. And let's talk a bit about the results and about the concrete artifacts we built. So a year ago, basically, we built a handshake visualization, which basically draws a sequence diagram of the just finished handshake in TLS. And this is basically, for us, it was a way to evaluate the interoperability between our stack on the server side and other stacks on the client side. And for others, it is actually a great way to learn about the protocol. So you can click here on the messages and then see the concrete values which your browser has sent to the server. And you can also see side by side the RFC specification, what it has to say about that message. So this is what we did roughly a year ago, and it had roughly 30,000 traces which we recorded and used for regression testing and to replay against our own stack. Then another artifact we built was a trace checker. How do I get to that? I hope that is big enough for you. So the trace checker is basically using our TLS stack as a specification rather than as an implementation. So the input to the trace checker is a packet trace file, so a pcap file, and the private key for that session. And then it reads the pcap file, which it already did over here, and reads the private key, and now it tries to replay each packet and looks, well, it presumes to be the server side for now, and then it looks what the client sends to it, looks what our stack would reply as a response to that client hello, for example. So here we have the first client hello, and then our stack produces an answer to that, and then compares the answer we generated with the answer which is available in the packet trace. So here is another event, which is which cipher seed and which protocol version to use, which is actually dictated by the pcap trace, because we just look ahead what version in cipher seed did the server choose on. And then the answer we send out to the client, so the server hello we send out. Then for this specific example, we also send out a certificate, or this certificate here. And then we dump out our internal state, because we need to dump the, we have the internal state here as an event again. And we continue with the client says something. Well, the client sends a client key exchange. It's an RSA cipher here, and dump out the internal state and so on. And going on, we successfully finished. And now I will do that on a second packet trace, which is a packet trace of a Heartbleed vulnerable server. And so the first message, again, is the client hello. The second message, is a version in cipher. And that is our response, the internal state, and then the internal state. And we received a Heartbleed while a handshake, so our stack decided to send out a fatal alert and close the connection, and that didn't match the pcap trace, so we see that output here. How do I get back? No. Thank you. So a third artifact we have is a transparent Bitcoin bait called the Pinata, which I will bring up in a moment. So we thought we need to evaluate the security of our stack, and how do we do that? We want to have some people looking at the stack. So what we set up was we got donated some Bitcoins, and we set them up and put on the private key in some service using our TLS stack. And once you successfully authenticate against our TLS stack, you actually get the Bitcoins. So you get the private key to the wallet. And we expose both the server side and the client side, and we even enable people to short circuit the server with the client side. So you can actually, on your local machine, do a socket cut or whatever, and just see how a successful session is set up, and the secret is actually transferred via your computer. But unfortunately, it's encrypted, so good luck with that. It is setting up a custom CA on startup, basically. So here's the CA certificate for its current lifetime. This has been online for roughly half a year. And there has been actually some interest. So several people tried to attack it using flaws available in other stacks. We got roughly 20,000 traces from 1,000 different IPs. The trusted computing base of the Pinata is actually very small because we can run the Pinata directly on Xen, so we don't need a Linux kernel or a libc or so. And if we compare it to a Linux system using OpenSSL, we actually end up in 4% of the trusted computing base. Let's talk a bit about performance. The handshake performance is comparative to OpenSSL and PolarSSL of our stack. So it is roughly the same. The bulk throughput is also very comparative to the other stacks. You see here on the x-axis the block size, and on the y-axis the throughput in megabytes per second. Again, comparing OpenSSL, PolarSSL, and our stack. And you can see that we are up to 85% of the speed of OpenSSL, basically. And we are sometimes even faster than PolarSSL. We do have various rollouts. We have implemented an S-tunnel or a stat replacement, so a TLS proxy which listens to TLS connections on the one side and then forwards the application data to a TCP service on the other side. We have an XMPP chat client using the client side of our TLS stack and is written purely in OCaml and is all terminal-based. The trace checker you just saw. Then we have a Certify, which is a certificate authority tool, so it handles certificate signing requests and certificates and can sign requests. To conclude, I think we engineered a TLS implementation using a rather radical approach for the systems and security community. Instead of focusing on performance and speed in the first place, we focus on clarity in the first place, and we use purely functional goodness to do so. Our implementation is usable both as a specification and implementation. We have a rather small trust computing base, reasonable performance, and rather concise code. And by choosing the language and the language style, we actually avoid the root causes of common flaws. So to conclude, I think we implemented a not quite so broken TLS implementation. More details are at nqsb.io. It's all BSD licensed code, and we're happy to answer any questions.
At Woot the other day, Adam Langley made a comment that I thought was actually pretty key about how on Android phones it's pretty hard to, for example, ship an OCaml runtime on every Android phone. So I was wondering if you think there are any opportunities to say, I don't know, redesign cryptographic libraries or do sort of new designs in a way that doesn't involve, say, shipping an OCaml runtime or some ways to sort of re-engineer existing code. Maybe this is what Boring SSL has worked on. I'm not really an expert. I haven't really looked at this, but I was just wondering if you guys had thoughts on this.
I do not want it to seem like I am poo-pooing this work. This is fantastic.
No,
if you
sure, yeah, no, I think this is great.
If you can get away with using OCaml, then quite possibly you should do. But on Android, for example, I've got not just to carry the TLS, but WPA supplicant, and IPsec tools and Raccoon and all this other stuff. If we went with something different, they are all written around the OpenSSL API. And so we can like cut and run and leave them to rot, but that's not really so normal. So I am burdened by many problems, so my answer should not detract from other people possibly following this one.
Sure. I mean, I was just asking if the authors had any thoughts on like what to do if you were constrained by sort of existing languages.
Well, the question is
if
really...
the answer is you really need to be moving to OCaml,
the question is slightly multifaceted. One thing is like, what do you consider to be the OCaml runtime? It's not like JVM. OCaml runtime is basically the runtime support, minimum runtime support for what OCaml compiler generates, which is baked into the binaries. It's easily portable to Android, and people are actually shipping applications for Android written in particular on OCaml.
Okay, so maybe that was a
by
bad
itself,
example.
OCaml is a fairly lightweight managed language, actually a very lightweight one. It's not at all comparable to something like JVM at all. But if you press the issue and ask like, yeah, what can we learn here beyond just OCaml? Many things. If you can just get a garbage collector and get away with it, it seems to be one of the easiest things to do with the largest benefits. But if you just get a garbage collector and then use another kind of similar memory managed language, which doesn't yield to kind of functional programming, you're still left with kind of slightly intertwined code logic. So to go the full way, I think you would have to use OCaml. You can use it piecemeal in different kind of contexts, but then you don't get all of the benefits, in my opinion, at least.
Okay, thanks.
Hey, Benjamin Berdouche from Hineria. Thank you for this work. I have a question about the API for TLS, because when studying different implementation, we can see that different APIs appear for every implementation. And in fact, in the RFC specification of TLS, there is no API written in the specification. Can you tell a bit about your API and how does it compare? I suspect it's much shorter and much concise than OpenSSL, for instance. But what can we do better in the future for new implementations and for the specification? Thank you.
Thanks for that question. Yeah, I think there's actually missing an API for TLS in the RFC because nowadays everybody develops, every TLS implementer develops their own API for TLS, which boils down to OpenSSL having maybe 1,000 symbols of the API, which is horrific, and there's no semantics to that. So I mean, you cannot say what should happen if you call those 5 methods in a row or so. Luckily, for example, the libSSL project came up with a libTLS API, which is much more concise. It contains maybe 10 or 12 methods for the server side mainly, and the configuration is also much simpler. And what we have is basically very similar to libTLS. So we have send, receive, open, close. And then we have one function to get a configuration context. And then we have, so we have this purely functional core, and then on top of that we have 2 different APIs. One is for LWT, so an asynchronous event-based system written in OCaml, and the other one is for MirageOS, which is an operating system we are currently developing at University of Cambridge, which basically enables us to run OCaml directly on Xen without libc and all that legacy.
And it turns out, just as we're speaking, somebody in the lab is working on a 3rd version, which exposes the OCaml library as a C shared library for Unix systems. But I wasn't supposed to mention this.